section 2.1 of the guided notes. And chapter 2 has to deal with absolute value. And absolute value is a often misunderstood concept when it comes to algebra. And let's just dive right into it. Absolute value, written as x with these brackets, represents the distance between x and 0 on the number line. And that's the reason why absolute value is always a positive number. So basically a positive number. And the reason that is because distances are not negative numbers. If you travel any distance, you're never traveling usually in a quantity of a negative number. So the absolute value, here's an example, right? If I have 0, the number 5 is exactly 5 units away from 0. Conversely, the number -5, here and here, is also 5 units away from 0. So the absolute value of -5, if we're just talking about the distance from -5 to 0 on a number line, is in fact 5 units, right? Here's -4, -3, -2, -1, 0, 5 units. So let's take a look at this table below, and let's begin to complete the values. So the absolute value, right, if I was plugging this in for x, let me rewrite it a little better. The absolute value of a -8, right, we're just simply talking about on a number line, how far is -8 away from 0? And of course, right, that would be 8 units, right? And same with the absolute value of -4, right? 4 units away. 0 is 0 units away from itself. 4 is 4 units away from 0. Absolute value of 8 is 8 units away from 0. So hopefully you've seen this before, and let's go on to the next section of the guided notes. Now, if you plot those points from above, right, at -8 we get 8, and at -4 we get 4. So absolute values do in fact have a graph, and you're going to find that their graph, after I plot all these points that you just have in your notes above you, the graphs of absolute values are in fact like a V shape. And we would call this basically the parent function. If you've ever seen in my room a poster called The Math Dance, it's up by the phone. That is essentially the shape of a number of parent functions. And like most parents, there's offspring functions, if you will. And basically the parent function for absolute value is simply f of x is equal to the absolute value of x. Every other graph basically is an offspring of this parent function for at least absolute value. So let's continue along our journey here, completing these notes. So f of x is equal to the absolute value of x is symmetric about the y-axis. Oops. Not sure why I did that. Bear with me a moment. Hold on. Here we are. Symmetric. That's why my fat fingers messed it up. Symmetric about the y-axis. And therefore is an even function. And that won't make a lot of sense right now, but we're going to dive into even and odd functions a little bit later in the year. But for the moment, this is an even function. And let me see, here we go. The domain of the absolute value of x is essentially the set of all real numbers, written as an interval, like so, or the set of real numbers. And the range for this particular parent function, you'll notice it goes from basically 0 and up. So as an interval, I'd write that as 0, comma, to infinity. Or basically the set of all positive real numbers. And that's not every single graph of absolute value, simply just the parent graph that has this domain and range. If the graph were slightly different, then that domain and range will also be slightly different. So let's go on to the next section. So as we graph absolute value functions, right, now in the previous page we looked at basically the most basic absolute value function, and that was f of x is equal to the absolute value of x. But it could have all this other stuff added to it that you see here. And as we dive into this, you will begin to see how some of this information affects your graph of the absolute value function. So I'm going to trace for you, basically in purple, right? This was our parent function. All right, that's the graph you were looking at before, and that's the parent function. Now, I've given an example here, and let's just plug in some values to see what happens, and then maybe we can make some conclusions about what k does, about what h does, about what a does, and maybe what b does. So let's begin. So let me think of a good point to start plotting. How about, I'm noticing that this is a -5 right here, and I'm going to pick something that's going to make this 0. So I'm going to try, let me start graphing in a different color. I'm going to pick for x 5. So if I plug in 5 to this equation, right, I'm going to get essentially 4 times the absolute value of 5 minus 5 minus 2. So 5 minus 5, of course, is 0, and 0 times 4 is also 0, and 0 minus 2 is a -2. So let's plot in red now this, if this is the parent, right, we're going to call this, say, this isn't a technical math topic, but we're going to call this the offspring absolute value. We've got our parent function and our offspring function, so to speak. So I'm going to find 5. Here's about where 5 is, and then we've got to go down to -2. So there's 1 point on our graph. So I pick 5 for my graph. Let me see what happens when I pick another point. Let's see what happens when I select 6. So I'm going to do the work down here. If I take 4 times the absolute value of 6 minus 5 minus 2, well, 6 minus 5 is 1, and 4 times 1 is 4, and 4 minus 2 is 2. So the next point on my graph is at 6, 2. Okay, so far so good. Well, I tried 5 and 6. Let me see what happens when I try 4. So I'm going to take 4, right, times the absolute value of 4 minus 5, because that's what I'm replacing for x, and then minus 2. Well, 4 minus 5 is -1, and the absolute value of -1 is simply 1, right, because -1 is 1 unit away from 0. So 4 times 1 is 4, and 4 minus 2 is 2. So I also get 2. So then I go to 4, 2, and you'll notice, right, the offspring absolute value function is a little bit different than the parent, but not much different. It is a Still a V, right? But it's a steeper V. And what else is different? It certainly looks like it's been shifted. How has it been shifted? Let's see. Well, it's been shifted. Looks like it's been shifted 5 units to the right, and like 2 units down. 2 units down. And wouldn't you know, right? There's a 5, and there's a -2. So, you know, chances are this stuff probably refers to which direction you're going, left or right, and up and down. And if I had to guess, this 4 here is basically stretching or compressing, right? That A probably stretches or compresses. And that's that might be ringing some bells from last year when we did similar stuff with lines, I believe. So I'm going to stop graphing at that point, and then I'm going to fill out some more information on this graph. The vertex of the parent absolute value function is at 0, 0. G of x is a translation which moves basically 5 units to the right. That's the conclusion we just made. And 2 units down. The other thing I kind of put here, right? This H and that's K, right? Here would be H, and there would be K. And what is our vertex of our absolute value function, right? Our vertex, hopefully you remember our vertex, right? That's the point at which these 2 lines meet. And our vertex winds up being 5 and a -2. So moving on to the next section of the guided notes, there's a lot here. But chances are, as you're observing more examples of these, you'll notice like, oh, the information in this formula can help me know how to graph this by hand if I chose. But Desmos will also graph these as well, just saying, but we usually learn to graph it by hand first before we use all the electronic tools. So the next section of the notes. So here we go, here's another example, and again, I'm going to draw for you the parent function in green. All right, this is what the parent function looks like in green. And you recall from earlier in your notes, right, the parent function was f of x was equal to the absolute value of x. Okay, so there's the parent in green, and for comparison's sake. And then in red, I'm going to start plotting this stuff. Now, the last section we saw there was some information about the vertex, right? The vertex we knew to be H and K. And basically, the vertex was H and K when the formula looked something like this. X minus H, and then there was this, and there was an A. This looks like a future poster on the wall. And then it was plus K. So it looks like it has to be a minus H. Hopefully you're seeing, well, that's a plus, right? But this is definitely H, and that's definitely K. So if I had to pick a vertex for my offspring function, my offspring absolute value function, it wouldn't be +3, right? Because the formula says it's minus H. So it's going to be the opposite of what you see there. It's our vertex is actually going to be -3 and 1. And if you want to see if this is actually true or not, all you have to do is plug in -3 for x. So let's try that right now. We're going to find the g of -3, and we're going to plug it into this function right here. So what is the absolute value of -1/2 times I'm going to plug in -3 for x plus 3. Close the absolute value symbol, plus 1. I know some of you are just seeing this for the first time, but basically we have to solve all the stuff that's inside the parentheses, and then we move to outside the parentheses, right? First, second, and then this would be the third order of operations. So first off, -3 and plus 3, you get 0. And what's 1/2 times 0? That, of course, is 0. The absolute value of 0 is 0. So you basically wind up with 0 plus 1. And there you go. You do, in fact, get 1. So let's find our vertex, -3 and plus 1. So that's somewhere, about there. And I just happen to know what the next points are here. But to find some more points, right, if I did -3, I'd probably try a few more. And given that this is a fraction, I would try to figure out ways for stuff to divide into nice things that weren't fractions. So I'm going to try next, let's try 1 for x, because 1 plus 3 is 4, and I know 4 divides by 2. So I'm going to try 1 for x because, right, I'm thinking I don't want to deal with fractions so much if I can avoid it. So let's plug this in. You have basically, I'm going to use a different color because I think we're getting too much red. You have essentially 1 plus 3, -1/2 of that, the absolute value of that whole mess, plus 1. So, right, this would be the first thing I solve. 1 plus 3 is 4, and 1/2 of 4 is 2. If I go to this second, but it's a -1/2, so it's not, if this is 4 divided by 2, that's going to be 2, but I can't forget that negative. So I'm going to essentially wind up with -2 plus 1. And -2, oh, you know what, I forgot. It's not -2 because I still have to do the absolute value of that. So the absolute value of -2 is 2, so it winds up being 2 plus 1, 3. So then I find 1 and 3, and that's about here. And on the other side of the graph, I'm going to try, let's see, if this was at 3 and I went to 1, there's probably going to be some symmetry over here at -7. So let me try -7 for x. So now, right, this work here was me confirming the vertex. This work here is me confirming that second point. And now I'm going to write right here basically the function, the absolute value of -1/2 times, and then for x I'm going to put -7 plus 3, absolute value plus 1. And so I'm going to do this part first, this part second, and then third. So -3 plus, or -7 plus 3 is -4. -4 times a -1/2 would be +2, and you wind up with the same thing, 2 plus 1. So at -7, you'll get 3, and hopefully you notice a nice symmetry as well. So here's our parent, and you can call this the child, I suppose, or it's got to be a technical math term, but it's essentially, you can see how the parent function relates to different absolute value functions. It all starts with the parent, and then you add or take away, and it shifts this thing left, right, up, down, squeezes it, or stretches it. Next section. Now, in the previous section, we looked at this particular problem. You had Let's see, where'd it go? You had g of x is equal to the absolute value of negative 1/2 times x plus 1, absolute value, not 1, x plus 3. Let me fix that. Sorry if you're following along and wrote that down. X plus 3, and then it's plus 1 on the outside, right? And in the earlier part of the section, you had, well, you know, these functions take the form of a 1 over b, x minus h plus k, right? So, right, we concluded our vertex here would have been h and k, right? This is always our vertex of our absolute value function. And then, so in this scenario, right, our vertex was negative 3 and 1. And a here would just be 1, right? If a is not shown, typically it means it's 1, because the multiplication of 1 is implied, and it's not always shown. But our b here, this is what it means when our absolute value of our b was 2. So what happens when this was the case is basically this, some stretching happened. This was a horizontal stretch of f of x, since b is negative. And because b was negative, right, in our example, that was negative, and I'm talking about this right here. That's also a reflection. It should be a reflection about across the y-axis. So a reflection occurred as well across the y-axis. Now the x-coordinate will be reflected in the y-axis and stretched. By a factor of 2, right? Because that's how much b was, right? There's our b right there. And then it was moved 3 units to the left. Right? In our previous example, we went to the right, but that had a minus in it. This example, it has a plus in it, so we're moving to the left. The y-coordinate also will move up 1. And how did I know? This is, k is moving up, and whatever h is, it's moving, I should say, depending on what h and k is, this is the up and down, and this is the side to side. So, in our case, we have a plus 1, so we're going to move up 1 unit.